All right. Now we're going to talk about a specific kind of force that's usually seen in a lot of balancing scenarios, and this is the spring force. And as the name implies, it's the force exerted by a spring, and we're going to model springs as ideal most of the time in this class, which means they follow a very specific force law. So, for a spring to count as ideal, it needs to follow a rule known as Hooke's law, which states that the force exerted by a spring will always be directly proportional to the distance you stretch the spring or compress it from its equilibrium position. And there is a negative sign to indicate that springs always oppose the stretching or compressing you have been doing. So we call this a restoring force from the spring because it tries to restore the spring to its original position. So, for example, if I stretch a spring, pull it to the right of its equilibrium position, the spring will exert a force left and try to restore it. If I compress a spring, pushing it to the left of its equilibrium position, the spring will exert a force to the right to try to return to that spot. The only location where there's no spring force would be its natural length or equilibrium spot. And the proportionality constant k in Hooke's law, where F equals k delta x, represents something known as the spring constant or the force constant of the spring. I usually call it the force constant to avoid using the word spring over and over and over again. And it's really a measure of how difficult it is to stretch or compress the spring because the units of that are newtons per meter or newtons per centimeter. It tells you how many newtons of force do you need for every meter of stretch you would like. So it's very common to visualize this as a slope because it's a graph of force versus displacement or force versus extension because newtons per meter is division, a rise over run. The force constant is a property of the spring itself. That's why it is a constant. So the same spring will have the same K for every trial. The only way to change it is to change out the spring or like cut the spring in half or do all sorts of things that are changing the spring itself. Now, if the spring doesn't follow Hooke's law, the spring is not ideal. I can't really imagine where this comes up and it's not explicitly like a physics C calculus question. Maybe there's like a does this spring follow Hooke's law question where you're testing if the stretch versus force is linear or not, but the spring will be ideal. You can always assume that unless if we tell you. So we'll go through a couple just typical spring problems here. We're only going to be dealing with balancing today. A spring with natural length 6 centimeters. Natural length, of course, means unextended, has a force constant of 5 newtons per centimeter. So again, newtons per centimeter, that is a force per unit distance. So this would be our force constant or our spring constant K. A block of mass 2 kilograms is then attached to the spring, and the spring extends a little bit before coming to rest. Justify why the spring extends after the mass is attached. Well, if we think about what's happening here, this block is at rest. So the weight of the block must be supported by something, and that something is the spring. So the spring is exerting a force on the block, and in order for the spring to exert a force, it must be extended or compressed from its equilibrium position. So the spring must extend to supply the necessary balancing force. So we'll see that even though there's a force law, a lot of times the springs serve that balancing role that tension has served as well. All right, let's draw the forces on the block during equilibrium. So, of course, the block has weight due to its interaction with the Earth. And then, nope, the block isn't falling towards the center of the Earth. There must be a balancing force, and it is the spring force in this case. So, Newton's first law equation would be spring force, and the gravitational force must be equal in magnitude. All right, let's calculate the distance the spring extends once the mass is attached. Well, we will apply our only equation we have, which says that in this problem, We have an equilibrium established where the spring is balancing the gravitational force. The magnitude of the spring force is K delta X. Do not include the minus sign in Hooke's law. We're usually using magnitude. The whole point of the negative sign is to get the direction correct. So notice that I didn't use like vector notation here, so we're just taking magnitudes. And then Fg is, of course, mg. We want the distance the spring extends, so that would be delta x. So dividing, we get delta x equals mg over k, which would be the mass of the block is 2 kilograms. So just to show the unit math here, 20 newtons of weight balanced by, can't remember anything, 5 newtons per centimeter. And that's equal to 4 centimeters. And notice this could have been determined sort of without doing math, that knowing that it extends 4 centimeters, because I know for sure that I'm attaching 20 newtons of weight to this system, and for every 5 newtons of force, we extend a centimeter. So 5 plus 5 plus 5 plus 5, or 5 times 4, would be equal to 20. So I got to extend 5 centimeters to provide that 20 newtons of balancing force. That's why we love springs. They're nice and linear. So how is that different from the final length of the spring? Well, springs can have length before and after. So this just tells you the displacement. So we're given that the displacement of the spring was 4 centimeters, or the stretch. So the difference between the final and initial length is 4 centimeters. So my final length would just be the initial 6 centimeters that the spring started as, plus the additional 4 centimeters the spring extended, giving me 20 centimeters. All right. What would be the new extension of the spring if the hanging mass is doubled or if the spring constant is doubled? So originally we had delta x equals 4 centimeters. Well, our force law that's relevant here is we said that our governing equation was the force supplied by the spring is K delta X. So if the hanging mass is doubled, that doubles the force exerted on the spring. Spring constant doesn't change. So as a result, the extension must double, right? Double the mass hanging, double the weight force, so double the extension to balance. So it would be 8 centimeters here. Then if the spring constant is doubled, well, here it's going to be the same mass, so the same force is needed, but we have double the spring constant. So if I'm getting twice as much force per unit extension, I don't need to extend as far to get the same force, so this is just a half. So that would be 2 centimeters, because it's half of 4. Notice these should make sense conceptually, right? Double the mass, double the extension, because linear, and then double the spring constant, half the extension, because the spring exerts more force for the same pull. All right, simple math time. When a block of known mass m1 is attached to a vertical spring, the spring extends delta x1. When a different mass m2 is attached, the spring extends delta x2. Derive an expression for the force constant of the spring in terms of m1 and x1. So, of course, we can draw some nice free body diagrams here. This is just the same force balance as before. To see better. Because again, those would be our relevant force laws, right? We have a spring force and a gravitational force here. That is going to bother me that this mg is not aligned, so let's fix that. And then we have the same thing going on over here. We just have a different mass and a different spring, so we'll just subscript. All right, so derive an expression for the force constant of the spring in terms of m1 and delta x1. Well, we know that forces are balanced on m1, so I can say that the spring force up on m1 balances the gravitational force down on m1. Spring force would be k times delta x1. Gravitational force would be mg for mass 1. So the spring constant k, just divide everybody by delta x1. And that's our k. All right. Now derive an expression for m2 in terms of everything that's not k. So we're going to probably just substitute this in. Well, let's repeat our process just with the other object. So we said that the force balance for m2 looks once again like k delta x from the spring balances the mg due to gravity. And we want to find an expression for m2, but we can't have k in it. So notice there is no k, so we have to substitute our value in. Our value for k was m1g over delta x1 times delta x2 is equal to m2 times g. And now we can do some cancellation because everybody brought g. So since something appears in every single term on both sides, we can cancel g. So this result actually does not depend on the planet you are on, which is kind of rare. So m2 is equal to m1 over delta x1 times delta x2. But this will actually be a lot easier to interpret if we change the grouping, just to show kind of what's happening here. So m2 would be equal to m1 times this fraction, delta x2 divided by delta x1. So our last part of this will be interpreting this result and why this should actually make sense. So using your expression for m2, describe the condition or relationship between delta x1 and delta x2 such that m2 is greater than m1. Justify why this result makes sense qualitatively. So we're asking, what do I have to do to this formula to make it so that the output m2 is bigger than the input m1? So notice that m2 is m1 times this quantity. Now, if you're multiplying something by a quantity and it's growing, it must be bigger than 1. So that would be our condition, is that delta x2 divided by delta x1 must be bigger than 1, because I'm multiplying m1 by something, and it's getting bigger. So if you're getting bigger, you must be multiplying by a number larger than 1. Now, this condition is easier to interpret if we just multiply both sides by delta x1, and this just tells us that the top of the fraction, delta x2, must be bigger than the bottom of the fraction, delta x1. So why does this make sense? Why is this the condition that makes m2 bigger? That we can conclude that? Well, if a greater mass is attached, you extend more, right? Because spring force is proportional to extension. So if there is a bigger extension with m2, that must mean that m2 is bigger than m1, because a larger balancing force was required for m2. Now, there's a lot of cool things you can do with this problem. I've done things like a practical with this before. There's lots of clever ratio things you can do here. Because notice, for example, if it all depends on this ratio. So if the spring extends twice as far for m2, then m2 is twice as big, for example. So this is totally because of the linearity of the spring force. And then lastly, we will do just a standard lab question. Hooke's law is really good for these best fit lines because it's linear. Group of students want to calculate the force constant K of a spring with natural length 10 centimeters. They record the final length of the spring after attaching various masses in kilograms. And we're going to use this data to find K. So I actually am kind of putting you into a box here because I had a vision for this problem. So I'm actually telling you what I want you to graph, which is apparently not the raw data. We want to calculate the magnitude of the force exerted by the spring on the mass as a function of the spring's extension delta L. So we're creating a new table here. Why is that? Well, we said that Hooke's law says that the spring force is equal to K delta X. So notice this is not a force and this is not an extension. So we do not want to graph that yet. So we need to somehow get a force and somehow get a delta X. And we can definitely get the spring force because we're just in equilibrium. So the spring force is balancing whatever mass was attached. So mg would be the spring force. It would be the same as the spring force. So that's an easy column because we have F spring is Fg, which is mg. So my spring force, just multiply everybody by 10, so 0.2, so I get 2 newtons, 4 newtons, 6 newtons, 8 newtons, 10 newtons. And what is my delta L? We'll move this just for clarity. Well, delta L, just by definition, is the final length of the spring minus the starting length of the spring. So the starting length of the spring is fixed. This was 10 centimeters, so we just subtract 10 centimeters off each of these terms to get the delta. Because if I start at 10 and end at 13, that would be plus 3. If I started at 10 and ended at 15, that would be plus 5, and so on. So subtracting 10 from everybody, we get 3, 5, 8, 10, 13. And notice now this looks exactly like Hooke's law because our data would look like F equals K times delta L. So we could put F in a box for Y. We could put delta L in a box for X, meaning the slope of this line would be K. So this is nice and linear for us. So, of course, you do not want to see me painstakingly plot points and deal with a scale because I am bad at it. So we did the mining off camera as per usual. I could have used more of the grid, but that's not really something we grade. So notice force was on the Y, extension was on the X. I gave my quantities units, newtons and centimeters. I scaled everything. I plotted the points, and I drew the best fit line, trying to go half above, half below, although this was a pretty clean data set. Then, whenever we're asked to do anything, I always just plug this into Desmos and linear regression it. We've been over how to do that before, but if you just want to do the slope by hand and count grid boxes, that's cool too. So this was my best fit line that Desmos spit out. This was the regression. So we wanted an experimental value for K. And from our equation, we said that K was just equal to the slope of our best fit line, which was equal to 0.796. What are the units? Well, the units are just the slope unit. So the rise was newtons, force, and the run was extension, or which is centimeters. So we could say that K was roughly 0.8 newtons per centimeter. Or if you want to do SI units, you can get the centimeters to meters by multiplying by 100. Because you'd have to do this 100 times for a meter, or 80 newtons per meter. So this was my intention, was that you just do it in centimeters, but if you're a newtons per meter purist, you can do that. And then last, I'm just showing you that even if you graph like the wrong thing, you can still recover stuff from Hooke's law. So suppose instead of graphing delta F versus delta L, the students graphed LF, or final length, versus force. Describe how this changes the slope, describe how this changes the intercept. Well, we need to have a formula to figure out anything. So we do know that the actual formula we graphed was F equals K delta L. And they're graphing LF versus F, so we need to solve this for the final length of the spring. So by definition, delta is final length minus starting length. So F would be K times L times final length minus K times the starting length. So K times final length is equal to F plus K times starting length. And solving this for final length, we got to divide everybody by K, and we get final length equals force divided by K plus initial length. So how does this work? Well, let's think about what were variables and what were constants. So L0, this was a constant, and LF and F were variables. So we could rewrite this as LF equals fraction multiplication. We can just factor this out, right? We could write this as a 1 over K times F to kind of force this into Y equals MX plus B format, plus L0. So this was really just me tricking you into practicing your linearization identification skills. So they graphed final length is a function of force. So what this means is that the slope is K and the intercept is L0. So describe how this changes the slope of your graph from part B. So originally the slope was K, and now the slope is 1 over K. So the slope is, do I dare try to spell reciprocated? Slope is now 1 over K. I'm not going to try to spell reciprocated. The slope is now 1 over K. So our slope is upside down. So the predicted best fit slope would be 1 over 0.8. And then how does this change the vertical intercept? Well, originally we had F equals K delta L plus 0. So there was no y-intercept. So now the y-intercept is equal to the natural length L0 of the spring. So that's just some linearization practice here. Even though there wasn't a lot of linearizing, it was more just showing that there's lots of different ways to analyze the same equation. Yeah, not too much to do with our basics of springs here. But that would be Hooke's law.